So what other kind of trees might we be seeing? We might be seeing an expression tree. We'll be seeing this later. So this goes back to basically a bit of what we were doing earlier. But each node contains an operator or an operand. The operands are stored in the leaf nodes. Operands stored in the leaf nodes. And the operators are the internal nodes, right? Parentheses are not stored because the tree structure will dictate the order, right? X plus Y times A plus B divided by C, right? So it's this equation over here that's slightly covered up. So the operators in the nodes at higher levels are evaluated after the nodes at the lower levels. Less important here. More important is the Huffman tree. The Huffman tree is something we'll deal with as its own big section later, but it's a way that we'll be able to encode characters that might appear in a text file. This is an example of what that will look like. We won't be making one nearly that big, by hand at least. But the most common thing we do is binary search tree, which brings us back to why we have this weird example where dog is the parent of cat and wolf. Well, the answer is, for binary search trees, the key for a binary search tree is that all the elements in the left subtree precede those in the right subtree. So this is the definition for a binary search tree. A set of nodes, so like what we have on the board, again, which I'll switch back to, but also this set of nodes, is a binary search tree if either of the true. Is this an empty tree? Well, no. So what about the other definition? If it's not empty, then the root has two subtrees, the left and the right, such that these are both binary search trees. And the value in the root is greater than all the things in the left subtree and less than all the things in the right subtree. So let's take a look at that. And this will basically hammer it home. So all these things are words. So dog becomes before cat in the dictionary, and it comes after cat in the dictionary and after canine in the dictionary, right? These come before. So according to the compare to operation that we do on these are less than. They come before. Canine comes before cat. Cat comes before dog. Dog comes before wolf, right? So let's take a look at my binary search tree on the board instead, which helps. So let's take a look at our root. 9 is our root. We have is greater than all the nodes in the left subtree, right? Greater than 5, 2, and 7, but it's less than everything on the right subtree. So everything less than the root is on the left, everything greater than the root is on the right. But furthermore, that's true for all the subtrees as well. So 2 is less than 5, and 7 is greater than 5, right? So this is a binary search tree because it's recursive. 9 is greater than 5, 2, and 7. 5 is greater than 2, but less than 7. 12 is greater than 9. It's also greater than 11, less than 15. So let's go ahead and see what would be examples of. So let's go ahead and see what happens as we modify this tree, if it's still a binary search tree or not. This is still a binary search tree, right? Nothing, we've deleted an item here. There's nothing that's changed. Otherwise, this is still a binary search tree. Putting 6 over here, right? Everything on the left is still great. Is over here is still less than the root. And furthermore, the 6 that I put here, that's greater than 5, so that's fine. However, if I were to put a 4 here, that is not a binary search tree. And why? Well, while 4 is less than 9, so it's on the right side of the overall tree. 4 is less than 5, so it should be on the left of 5. Okay, so and furthermore, it's definitely less than 6, so it should be, even though it's on the right over here, it's not to the left on the left side of 5. What about putting it here? That's not going to work because 4 is greater than 2. Even though 4 is less than 5, 4 is greater than 2 should go on the right side. So this will work because everything to the left of 5 is less than it, and everything to the right of 2 is greater than it. Okay, so it gets a bit tricky sometimes checking it, but once you get to the field, it makes sense. Remember, you're looking at basically at every single subtree as its own individual unit, right? 9 is the root of the tree of its own tree, and right, so everything to the left of 9 is greater. Everything to the left is less than. Everything to the right is greater. For 12, everything left of 12 is less than. Everything over here is greater than 12. Over here, everything to the left is less than 5, greater than 5. And over here, everything less than 2 goes over here. Everything greater than 2 goes over here. So the property is recursive. Okay, what about if I were to add something like, again, if I were to put 13 over here, that's not going to work for multiple reasons. Well, for one reason, right, it would be to the left of 12. So everything greater than 12 would have to go to the right of 12. So that would have to go here. But it wouldn't go here because it would violate being everything to the right of a root being greater than the root. Right? 13 is less than the root over here, this node over here, so it has to go to the left over here.